let's discuss the system design of Uber or any other cab booking system. So we'll see few major parts of the system, like how the user searches for cab and gets the fare estimate or ETA. Then how after placing the ride request, drivers are matched. Also, how do you ensure that there will not be any double booking in the system? Like one rider should be matched with only one driver, and one driver should match for only one ride. We'll come up with a scalable and fault-tolerant design here. First, I will list down the functional and non-functional requirements. For the functional requirements, I have ordered them from the user's perspective. So there are two kinds of user in the system, rider and the driver. So first, rider searches for the cab with source and destination. Uber shows ETA and fare estimate for different types of cab. Let's say Go, Moto, Sedan, etc. Rider then books a cab. Uber matches nearby drivers. Then Uber sends requests to all the nearby drivers. Basically sends notification to either accept or deny the ride request. Driver can accept or deny the ride request. If the driver accepts, driver will navigate to the pickup location. After the pickup using some OTP or something, driver navigates to the drop location. Then driver ends the trip and rider makes the payment. So this is the main flow of Uber or any other cab booking system. There are few out of scope requirements I have listed down, like profile creation, ratings, like driver and rider both can rate each other, notification service, monitoring and analytics. So these are some of the requirements that any large scale system will have, but we'll not focus on these things here. We'll focus on mainly this core functional requirements. Next, come to the non-functional requirements. So non-functional requirements are the qualities of the system or how the system should behave. First of all, the CAP theorem. So whether the system should be highly available or highly consistent. So here part of the system will be highly available and part of the system will be highly consistent. So this system should be highly available for the search, cab search. Let's say finding the ETA, fare estimate, etc. So the whole cab search part will be highly available. Highly consistent for driver matching. And what that means? That means no double booking should happen in the system. Like one ride will match with two drivers or multiple drivers, or one driver is matched with two rides or multiple rides. This kind of scenario should not happen in our system. Latency should be as low as possible. Then durable, we'll be storing or persisting the ride information, ride details in our system for future reference. Scalable. So of course this is a highly scalable, this will be a highly scalable app. So we need to consider about the peak hours when the ride requests will be much more, and also for the new users. So new users will be onboarded to our system, right? So we need to be able to scale the system for these peak hours and for new users. Next, let's discuss about the main entities in the system. So there are two types of users in the system. One is the rider and one is the driver. So these two are the user entities. Next, the estimate, right? When user is searching for the cab, the user will get one estimate with the ETA and fare estimate. So this is the estimate object. Next, the main ride object, ride entity. Next, the location. So we can see, the rider can see the driver's location and driver also can see where the rider is, right? Next, the cab. So there are different types of cab in the system like Go, Moto, Sedan and all this. So if we are talking about a different cab booking system like Ola, Rapido, so then there will be different types, but mostly cab will be one entity here in this system. Next, talk about the APIs. So the main APIs these are not the final API design, but this is something to start with. So let's say the first one is the get fare estimate. So that will be a get API, get slash estimates. It will take the parameters like source latitude, source longitude, destination latitude and longitude, right? And what it will return? It will return the estimate and ETA for different cab types, right? Let's say it will return, there is a response object will have estimate ID and estimate and ETA for different cab types. Next, booking a ride. So riders will be able to place a book request with post/rides API, and what it will take? It will take the estimate ID from here and it will take the cab type. So because in this result we have the estimate for different cab types, right? So rider can choose the particular cab type and place this ride request. Next, for location updates, let's say we have a post/location/update latitude and longitude API. Driver will be able to accept or deny ride request. That will be a patch call because here when the server your rider is placing a book request, placing a ride request, ride entity will be created in the system, right? So to accept or deny ride request, so that will be a patch call. So patch, let's say /ride/driver/accept. Okay. So it will take the ride ID and the operation, whether it's a pickup or drop. Next, last one is for the rider. Rider will be able to make the payment. So that, let's say, will be post/payments, ride ID and payment info. I have kept this one simple here for this discussion. Next, quickly have a rough estimation, rough scale estimation for this system. Consider there are 100 million total riders in the system and 10 million of them are daily actives. So 10 million daily active riders we have and 2 rides per user on an average. Also, let's say 1 million drivers in the system. So how many ride requests we are having per day? 10 million daily active riders and 2 rides per user, right? So that means 20 million ride requests per day. So 20 million is 20 into 10 power 6. And if we assume 10 power 5 seconds in a day approximately, so that will be 20 into 10 power 6 divided by 10 power 5, that is 200 TPS or transactions per second for ride requests. If we consider peak time, so let's say 3x or 5x times of this, so that will be, if we consider 3x and then 600 will be the TPS. Next, location updates. So here I am just for simplicity, I am considering only the location updates for the drivers because driver is always moving, right? So location update, let's say every 5 seconds drivers will update their location. So there are 1 million drivers. So 10 power 6 divided by 5, that will be TPS for location updates. So 200k is the TPS for location updates. So here I just have covered the location updates for the drivers. If we consider the location updates for riders, so that will be much more. Now let's come up with a high level design here. So of course we'll be going for a microservice based architecture because we have seen that there are different requirements and responsibilities in the system. Few parts has to be highly available and few parts has to be highly consistent. So these are the major services in our system and we are using API gateway for authentication, authorization, API routing, load balancing, rate limiting and all this stuff. So the first service we have is the estimate service. Using that, rider can get the estimate like the fared estimate and the ETA for source and destination. So how the estimate service will find out the source and destination? So let's say there is a map service, we can use a third party or inbuilt service for that. So given any source or destination location, it will find out the distance and also based on the other conditions like traffic congestions and etc. It will figure out the ETA and based on that estimate service will come up with some fare estimate. Next, booking a ride. So there is a ride service using which rider will be able to book a ride. Now what this ride service will do, it will create one entry in this ride database. And let's say there is this ride table and it will store the ride ID, source and destination, basically source latitude, longitude, destination latitude, longitude, rider, driver. So initially driver is not assigned, right? So this column will remain empty. This status. So status can be, let's say, requested, accepted, started, or finished. So when the ride request is created initially, the status will be requested. Now what ride service will do apart from creating this ride entry in this table, it will forward this ride request to this driver matching service. Driver matching service is responsible for finding out few nearby drivers and sending the ride accept request to them. So if the driver denies the ride request, driver matching service will move on to the next driver. So driver can accept or deny the ride request using this call. And let's say if the driver accepts the ride request, so then driver matching service will send this driver details or driver ID to this ride service. Ride service will update the driver ID in this ride table. Also, the driver details will be shared with the rider. Now, after that, driver will navigate to the rider's location, will initiate the pickup, then it will navigate to the drop location, and then it will initiate the drop off. So this is defined by these two calls, either a pickup or drop off call. After that, rider will be able to make the payment for the ride using this make payment call, and it will come to this payment service. Now the payment details also we can store in this ride table, like with the payment status column. Also we can store it in a separate table altogether, but I have not shown it in this diagram. Now the main part here is how the driver matching service will find out the nearby drivers. It has to know the location of the drivers, right? So let's say these drivers are sending the update location events to this location service. So driver will mostly always be in moving conditions, right? So let's say drivers are sending their locations every few seconds, let's say every 5 seconds to this location service. Location service is storing this location data in this locations table. With this user ID, this is the driver ID basically, and the timestamp and latitude and longitude. For this timestamp, this is the latitude and longitude. So next, driver matching service use this locations details to find out the nearby drivers. Rider also has to update their location because drivers also can see the rider's location. But rider will not always be in moving conditions, so rider updates will not be that frequent. Now we see this green calls should be WebSocket connections. We'll see why. So first of all, this frequent location updates. So driver is updating their locations frequently every few seconds, and this is from client to server call. Server to send ride accept requests to the drivers. So this ride accept request driver matching service is sending to the driver. That is from server to client. Server to send real-time updates for ride status change. So if we use a separate notification service for that, that will add some delay. So for this we see like it is better if we have a bi-directional connection. But there are other solutions as well using SSE or server sent events. So driver matching service can send this ride accept request using SSE. So but problem is SSE is not supported in all mobile devices. Also WebSocket has lowered latency. But we have seen that the communication is bi-directional. If we have a bi-directional connection, that will be easier for us. So that's why we are going for a WebSocket connection. Next, see how we handle the frequent driver location updates. So there are 1 million daily active drivers, right? And they are sending location update every few seconds, let's say 5 seconds. So 1 million is 10 power 6. So that means 10 power 6 divided by 5 is the TPS. 200k is the TPS, which is very high. Now SQL database supports max 10k TPS for a single node. DynamoDB supports up to 100k plus. Redis supports up to 1 million TPS. So we see that if you are using any SQL or NoSQL database, our TPS requirement is not satisfied. So can we do batch updates to database to reduce this write overhead? So we'll not update this location DB for every location updates. We'll batch it in this location service. We'll update in a batch. So what will be the problem here? The problem is it will introduce some delay in this driver location updates, and driver matching might not be appropriate. This driver matching service is basically using this driver locations to find the nearby drivers, right? So if the locations are not updated in real time, then the driver matching will not be appropriate. So first, now let's see how the driver matching works. So user sends the source and destination location, right? So let's say we have the source location. Consider this is the user location. So here, instead of latitude, longitude, I have written XY in few places. So this is the world map and this is the user location here. So let's say the service will find drivers within 2 kilometer range. So this is the user location. Let's say we'll create a 2 kilometer radius circle around it, and we'll try to find out the drivers within that circle. So if this is XY is the user location, then from x minus 2 to x plus 2, y minus 2 to y plus 2, this is the range where we'll try to find out the drivers. So consider this location DB here. We had user ID, timestamp, latitude and longitude. That means for each timestamp I am storing the latitude and longitude. So consider the latest latitude longitude only for the drivers. So here I am using just the latest latitude and longitude, and this is a simplified query. So consider select driver ID, latitude longitude from location where latitude between user latitude minus radius and user latitude plus radius, and longitude between user longitude minus radius and user longitude plus radius. Basically between this two and this two range we'll try to find out the drivers. Now what's the problem with this query is driver locations, there are 1 million drivers and each driver is updating their location every few seconds, right? So consider 1 million drivers, and if we need some indexing for this latitude and longitude, right? But in a database we can use only one index at a time. So if we use index on latitude, then also the result will be huge and the query will be very slow. So what we can do is we can have two separate tables, one for latitude, one for longitude, and first one will be indexed on latitude and second one for longitude. So we'll find the result from both the tables, and then we'll take the intersection. So that also will be computationally intensive, right? So let's see if we can have a different kind of indexing for this solution. So basically for this kind of geospatial requirements, we use geo-indexing. So there are different types of geo-indexing. One is the geo-hashing or quadtree. So let's quickly discuss what are these two. For this geo-hashing, let's say this is the world map, right? This is the flat 2D map of world. So this is the level 1. This is the whole map, and whole world map is divided into 4 parts. In the level 2, each of this chunk basically is again divided into 4 chunks. In level 3, again that one chunks is divided into 4 chunks. And in this way, we can decide how many levels we'll be using, and we'll divide the chunks into multiple smaller chunks. In case of quadtree, what we do is similarly we'll divide the whole world map into 4 parts, and this is based on the locations. So let's say in the first chunk we have 1 location, in the second chunk we have 2 location, in the third one we have 1, in the fourth one we have 2. So it's just for simplicity we have shown only 1 or 2 locations here, but let's say we have a limit. If the number of locations goes beyond that limit, we again further divide the chunks into multiple smaller chunks. So here in the second chunk, you see, like that's why we have divided it into 4 parts again. So here for this 2 part we see one locations available. For the third chunk we don't need to divide it again. For the fourth part, here we have divided into 4 parts, 4 chunks. But in the again, you see in this chunk also we have 2 locations, right? That's why we have divided it again. So that way we just need to come up with a limit, like if the chunk location size goes beyond that limit, we'll divide it again further. So here we have shown it in this design, in this diagram as well. Let's say this is the whole world map, and it has been divided into 4 parts. So the first one we have just A, and the second one it is divided into 4 parts, and we have this C and D here. B is not divided again. This one, the last one, is again divided into 4 parts, and the first chunk of this part is also again divided into 4 chunks, right? So here we have this 4 and only E and F present in the last 2 chunks. So these are 2 different ways to divide our world map into small chunks. But we'll see quickly now why it is useful. So let's say these are the chunks here. So of course these chunks will not always be defined by these straight lines, but for simplicity I have drawn it using straight lines. So let's say our user is here. So this is the user location. We'll draw a circle of, let's say, 2-kilometer radius, and we'll find out what all chunks are basically falling within this 2-kilometer radius circle. So basically this 1, 2, 3, 4, 5, 6, 7, 8, 9. So these chunks are adjacent chunks of this user location. So if we have the user location, we can find out like which chunk the user belongs to, and then we can get the adjacent chunks of this user chunks, right? And we'll just find out the drivers that belonging to those adjacent chunks only. So basically we have limited our driver search within this adjacent chunks. So let's say this map service will use some geo-indexing or quadtree indexing based database. We have our right source location. So we can get the chunk of the source location from the map service. We get adjacent chunks from map service. Then we'll get the list of drivers fetched from location DB who belongs to those adjacent chunks from this location DB. Order by distance, limit by X, let's say 10 or 15 drivers at a time. Driver matching service then will send requests to drivers one by one. One driver rejects, we'll move on to the next one. If driver accepts, send request to ride service to update the ride details with the driver. Ride status changed to accepted. Then after that, we'll also send notification to the user or the rider. Now what problem we have in this solution? So we have the source location ID, the rider source location ID. Using that we got the chunk of the source location, and then we got the adjacent chunks, which is fine. But then we want to find out the drivers who belong to those adjacent chunks, right? But here in the location DB we just have the latitude and longitude, right? Because driver is just updating their latitude longitude in this location DB. How do we find out which all drivers belongs to those adjacent chunks? So there will be 1 million drivers updating their location, right? So do we need to search through all the drivers? No, right? And take help from map service? Like for each driver will find the chunk they belong to? That's a poor decision, right? So we should not go ahead with this poor approach. Let's use a database with geo-indexing capability. So for this location DB, we can use a database that is geo-indexing enabled. So Postgres has geo-indexing capability with PostGIS. Also Redis has geo-hashing capability. But we have seen one problem here when we discussed about the location updates, right? There are 1 million daily active drivers and they are updating their location. So 200k is the TPS. So normal SQL and NoSQL drivers will not be enough. So can we use Redis for location updates? And also then for nearby driver search. So one thing is, in this location database we have to store the, for each timestamp, what is the driver location. That is fine, but to find out the nearby drivers we just need to know the latest location of the drivers, right? So in the cache we can store this, just the latest location of the drivers. Driver ID, latitude and longitude, let's say each 8 bytes, so that means 8 bytes into 3, 24 bytes, and approximated to 25 bytes. So for 1 million drivers, 25 into 10 power 6 bytes, that is 25 megabytes, which is very low. We can store the latest driver location in Redis, which is a distributed cache, fine. Now we can update all this location events, like for each timestamp what is the driver location, right? This events we can store in this location DB, which can be a Cassandra or Dynamo DB. Now let's see this updated design here. So location services updating the latest location of the drivers in this Redis, and also the all the location events for each timestamp is getting updated in this location database. This can be updated in async way. And also the driver matching service is finding the closest drivers from this Redis using this geo indexing. So Redis has this geo add and geo search option, which can search within a radius. Now what happens if Redis fails? We know that Redis is a distributed and it's very rare that Redis will fail, but in any case we should have robust monitoring and failover strategies. And system can recover very quickly after failure because driver is sending the location update every 5 seconds, right? So we'll quickly recover from the failure even if it happens. Now next one is driver matching consistency. So we had a requirement that we should not allow double booking in our system, right? So double booking as in one ride multiple drivers and one driver multiple rides. So driver matching service is sending ride accept request to the drivers, right? So for one ride, this driver matching service should not send request to multiple drivers. So for that, we are sending requests to drivers one by one, right? So first it will send a request to one driver. If the driver denies, it will move on to the next driver. Also, one ride request should be handled by one driver matching service only. So we should scale the driver matching service based on the ride ID. We can use consistent hashing for that here. We scale the driver matching service based on ride ID using consistent hashing. Only one server handles one ride and server sends requests to drivers sequentially, like one by one. One denies, sends request to the next driver. So no two drivers will be booked at the same time for one ride. Now come to the second requirement. One driver, multiple rides. So we have already scaled the driver matching service based on ride ID, right? So let's say two ride requests went to same service instance. Both got adjacent driver lists. Possible that one driver is present in both the lists, right? So we don't want to send multiple ride requests to one driver simultaneously, because if he accepts, there will be double booking, right? One driver will accept ride requests for different rides at the same time. So that is a double booking. So we need to have some kind of locking here. So can we have a service instance level lock? So one service instance doesn't send requests to one driver for multiple rides simultaneously. This will work in service instance level. But let's say two write requests went to two different service instances. Both got their adjacent driver list, and possible that one driver is present in both the lists, and that lists are handled by two different service instances. So here this service instance level lock will not work, because multiple service instances can log the same driver simultaneously. So what is the use of this lock? We don't need this lock, right? So only within a service instance this lock will work. So our next solution is we can have a database level update, right? So we'll update the database for driver status, and we can have a application level lock for TTL or time to live. So we'll update the driver status to be outstanding request, because we have already sent a request to the driver for one ride. We'll change the driver status to be outstanding request. We'll manage a lock in application. If the driver accepts, we'll update the driver status to be accepted or in ride. If the driver denies, we'll release the lock and update the driver status to be available. Now, what happens if service instance crashes? This driver status will remain in this outstanding request state, right? So we need some extra work to clear this. We need some extra cron job to find such driver status, and we have to clear that out. So that is an extra overhead. The solution here is using a distributed lock in Redis with TTL. So driver ID can be locked in Redis for let's say 10 seconds. So this is the updated design here. So we are using the same Redis we used earlier. So here in this Redis, we are storing the latest location of the drivers, and driver matching service we are fetching the closest drivers, right? Now we are storing one distributed lock on driver in this Redis, and we'll check if driver has any outstanding lock. So for this closest driver, we'll check one by one if the driver has any outstanding lock. If not, then only we'll lock the driver, we'll move ahead. Now one more quick thing is, how do we scale this write service, right? This write service. So we can make this stateless, because this is just taking the write request. It is creating one write table entry here, and it is forwarding the write request to the driver matching service. So we can introduce one queue in between, right? This is a write matching queue. Write service will put the write request in this queue, and driver matching services will listen from this queue. So using that, this write service and driver matching service will not remain tightly coupled. This will become loosely coupled, and they can scale at their own pace. Now, few quick things before we end our discussion. So, how frequently drivers need to send the location updates? So, earlier we have seen that driver is sending the location update every 5 seconds, but doesn't need to be fixed. We can have some adaptive strategy in client using some on-device sensor and client algorithm. So let's say the driver is not moving. We don't need to send updates then, right? And if the driver is moving slowly, then we need to send less frequent updates. Only if the driver is moving very fast, then we have to send the updates very frequently. So this kind of adaptive strategy we can develop in our client app. So now we are almost done with the design. Let's discuss one quick thing here. How to scale geographically and for peak hours. Basically, we'll be sharding the system geographically. We'll use geo-sharding, consistent hashing and all. And we'll have copy of the systems, this system, the final design we have here. Copy of this same system deployed in multiple data centers with data replication worldwide. With that, we'll have a fault-tolerant and scalable system design of over.